In this video, we'll demonstrate how to differentiate a power series term by term. I've chosen as the power series summing from n from 0 to infinity. I have powers of x. I'm alternating those powers. I have 3 to the n times n plus 3 in the denominator. I've written out a few of the first terms of the power series, and you can notice that the first term here is 1/3 is a constant, and then I have a linear, quadratic, cubic, and higher degree terms appearing in the power series. In a previous video, you may have seen us using the ratio test to show that this series converges for all x less than 3 in magnitude. So the absolute value of x should be less than 3. It will diverge for x bigger than 3 in magnitude. In order to find the derivative, all we need to do is differentiate term by term. What that means to do is to preserve any coefficient. In this case, any expression involving just n alone is a coefficient. It's just a constant in that term, and I've copied that into the series below for its derivative. Then, using the power rule, I have to differentiate the x to the n, and that's just using the familiar power rule. So I'll bring down the power, and I'll go down 1 degree, and I'll have n times x to the n minus 1. Now, I haven't written the limits of the sum here, and I'm going to start with n equal to, well, we had n equal to 0 here in the beginning, so presumably we'd start at n equal to 0 in the bottom as well. However, it's going to be a 0 term initially, because when I take n to be 0, I now have a coefficient with an n in it, and that would make the entire coefficient 0. So just to illustrate that this term won't have a constant term, or at least a term starting with n equal to 0 anymore, I'm going to start the series at n equal to 1. We should also compare what it looks like to differentiate this expression above as it's written out term by term. When I differentiate the 1/3, I'll get 0. When I differentiate this linear term, I'll get a constant term. Now that's 1 over 3 times 4. And I differentiate x squared, I get 2x with whatever coefficient was already there. And now I get 3x squared from the x cubed and whatever coefficient was already there, and continue on for the remaining terms. We get a new series now. That series is guaranteed to converge absolutely on the same radius of convergence as my original series. We don't need to use the ratio test or any other method to test for that. That's going to be automatically true. So it will converge absolutely for the same radius of convergence. Just to illustrate, we can evaluate this series at x equal to 0, so the derivative at 0 will now be this new constant term. All the other terms will be 0, and I'll have minus 1/12 for the derivative at 0. If you need to, you could differentiate again. So we could take the second derivative. In this case, I'll preserve any existing coefficient that includes the n that we got from the power rule. And then I'll just differentiate x to the n minus 1, so I'll bring the n minus 1 down and lose 1 degree. It'll be x to the n minus 2. Just as before, I would presumably be starting at n equal to 1, but when n is equal to 1, this factor would be 0, and there's really no need to start there, so I'll start at n equal to 2 and go to infinity. Writing out a few terms, the constant term now is 0, and I just apply the power rule on the linear term to get 2 in the numerator. I apply the power rule here, I get 6x now, and we would continue on in the same fashion. And if you needed to, this series would automatically converge absolutely for x less than 3 in size and magnitude, and you could calculate f double prime of 0 just as easily as we did above. All these terms of higher degree would vanish, and it would be 2 over 3 squared times 5, which is 2 over 45.